You were told you were.
Yes, which is an institution I don't believe in.
The irony of that is also that you were literally like the public face of, and we're all the same.
Yeah. Just, so I started the screen recording, just so you know, so anything you say is going to be enshrined forever.
I'll say a lot more.
Yeah. Okay. Okay, so we have been just spending a little time applying some of this event graph stuff to a slightly different domain than is usually the case. The historically, the discrete event approach arose in order to overcome some of the restrictive assumptions that arose from many queuing-like models. In fact, there's a whole domain of probability theory called queuing theory that deals with analytic solutions to the kinds of problems similar to what we've been looking at. And the problem there was that the analytic solutions would only take you so far. So at some point they came up with this idea of simulating it rather than trying to get an analytic equation and stuff. Having said that, we are dealing a little bit with equations in this domain, namely, modeling things that move around. And one question which sometimes arises, sometimes sooner, sometimes later, is what if something happens while you're traveling to your next destination? So what? Let's see, pen color red. Okay, so if you remember, the basic maneuver that we've been modeling is that if I have a unit located at a certain destination and it can travel according to an equation of motion, and we've been looking at the simplest equation of motion, namely constant velocity, and as we've seen, there's basically one event to start and another event to end. Okay, so, and because we know how the event list works, if the time it takes to get from this location to this location is the delay on the scheduling edge for the two events, then time moves forward by this amount by the time the thing shows up. And the question comes up, again, sometimes sooner, sometimes later, is that what if something happens in between? So, so basically, if there's going to be an interaction, then there needs to be some kind of detection. In other words, and that detection can be literally a detection or it can be sort of a figurative one. So for example, if there's some kind of barrier that you would run into, then the detection, as it were, would be if you smack into it. So we can think of it that way. Or, but generally speaking, for an interaction to occur, there has to be some sort of energy transfer, as it were. There has to be some kind of detection. So we're going to look at the simplest version of that. And again, hopefully by now you're used to my approach of doing things as simply as possible and then seeing what the shortfalls might be and then trying to enhance it. Okay, so how can we approach this in a discrete event way? So again, we're going to start with the simplest case. So what is the simplest case? The simplest case, I think, is the idea is that we have some kind of sensor, and let's say that it's just to be as simple as possible, it's located at the origin, and it has a footprint that's circular. Again, all of these are assumptions which can be modified as the case may be. But so we have this sensor, and And the idea is that it's just going to be some kind of circular thing. So sometimes in the case of stationary radar where it's kind of spinning around in a particular location, this is kind of a reasonable approximation of what's going on. And typically when you're modeling sensors like radar, there's typically a maximum range of detection, and the details of all that get a little bit dicey if you start to dive into the radar range equations and all that, and signal noise ratios and things like that. And we're just going to make it much simpler here. So the idea is that, so supposing there's this sensor here, and I have my mover guy, and he's going to be going to this location here. And as just basically, here's what we're going for. Is it when will the target enter the sensor's range, and when will it exit the range? Two natural questions, because until it enters the range, there's no possibility that the sensor could ever detect it. And once it exits the range, then the only way that you can kind of have any idea of where it is if you do some kind of dead reckoning calculation. But just with this simplistic, but reasonable, I think, approximation, before you enter the range, then there's no possibility of detecting, and after you exit the range, then you don't have eyes on it. Again, just natural. And so the questions kind of come up: does the target enter the range at all? If so, when and where? And then when does it exit the range? If so, when and where? Now, once it's in the range, then the question is, how do you detect it? So in other words, all of these involve the exchange of energy. So in this simplistic model, outside of the maximum range, there's no signal return, as it were, and then inside that there is. But then often the way that these work is at the maximum range, the signal return is relatively weak, and so you may not see it right away. Alternatively, if you think of your sensor as just, say, looking out for something, then even if something kind of comes into your field of view, you may not see it right away, depending upon other factors like environment and background noise and stuff like that. So again, all of those things are things we're going to not deal with immediately, because if we can't answer these questions, then the whole thing is pointless. So, and some of you may be thinking, well, maybe it is pointless, so let's move on to something else. But sorry, you don't get a voice in this. Yep, that's just the nature of the nature of this relationship. I get to call the shots here, at least until the end of the quarter. Okay, so here's the canonical sequence of potential events that we have. So here's our mover, starting at the red X and then kind of ending up here. And so we've already identified the start move and the end move events. And so from a discrete event perspective, therefore, what we're looking for are events. I'm going to call one enter range and the other one exit range, just for now. And then in between, again, just due to the nature of how these things typically work, at some time after the range is entered, there actually will be the detection. And then sometime after that, there may be an undetection. In other words, even within the field of view or the maximum range, there may be a point where you're actually not getting a signal return. And so so even though it's kind of in there, you're still having difficulty seeing it. There's a whole body of work that has to do with how sensors detect things. And you probably encountered those. So there's like a ton of research both on physical sensors as well as theoretical things, and there are just whole monographs and whole areas of study that look at this problem of how something gets detected. In my experience, there has not been a whole lot of work done on how to model the time between when you detect it and when you lose it. For some reason that, and in a way it's kind of understandable. If you're looking at some type of defense system, you want to be able to detect them. And, and that, if you can do that quicker, then your countermeasures will be able to be deployed quicker, and therefore you'll have a better chance of actually, intercepting or destroying whatever the threat might be. So that's understandable. So this undetection thing is kind of something which comes up naturally in a simulation world, but again, doesn't seem to have been studied that much. Okay, so here's the thing: is there a way that we can figure out what's going on here without having to draw a picture? Again, like if we have to kind of hold a picture up to the computer, that's not really going to work quite so well if we're trying to run a simulation. So how can we do this? And I'm going to switch to the whiteboard. Maybe. Oh wow! I can see nobody's used it since. And of course, there are no markers, so maybe it'll work. We'll see. Okay, so here's the. So we have something at the origin, and it has a radius of r. So we have our mover here, and it's shooting for a destination, and let's say that we've computed the velocity. So again, that's, as we've seen, that's kind of a complicated deal, and we're going to start moving at time 0 just to keep things simple. And what we're interested in is can we determine, can we determine when this thing enters here? So how might we do that? Well, what is our equation of motion? Now, because we're starting at time 0, it's just a little bit simpler. And remember, x0 and v are both vectors. So while we are moving from one point to the next, at any point in time, this is where we are. And so what do we know about the...
You would just compare the Euclidean distance to the center point of the detector to the current position.
Exactly.
That tomorrow.
Yeah. So in other words, we are going to detect it, or I mean the enter, we're not detecting it, but when our equation of motion is exactly equal to r. So now here's the thing, is that now we know what this is because this is the state of our mover. We know what the velocity is because that's also the state of the mover. And presumably we would know what the range of the sensor is because that would be a parameter if we were doing this as, so the only thing that we don't know is t. And so the question is, can we solve this for t? Okay, now remember this is our Euclidean distance, that is, this would be the square root of this squared. And so as square roots are a pain, so, so this is where you know, we haven't done anything. We might have introduced some extraneous roots, by the way, just whenever you do this. Okay, so now how can we figure out what this is? Well, remember that the norm of a vector is, or a square, is going to be, well, there are several ways of describing it, but one is simply the inner product of the vector with itself. And so what this becomes is the inner product of and that's equal to the square of r. So now, if you think back, maybe the inner product of the inner product has the distributive law, and so we can distribute this. So in other words, if we multiply this out, the inner product of x naught with itself twice the inner product of x with the velocity, and then t squared times the square of the magnitude of the velocity, which happens to be also the square of the speed. But this inner product here is, you know, we can't just kind of go back to the speed, but we can in this particular case. So what do we have here? What is unknown? We know everything in this except for t, and this is a quadratic. So can we solve a quadratic equation in t? Well, there are a couple ways of doing it. One is to remember our b squared minus 4ac over 2a, whatever that is, which I can never remember. But what I can remember is to complete the square. So that's how I typically like to do it. So I kind of just write this as and then I bring the constant over to the other side. And then, well, and then what we can do is we can then divide this guy to and then you remember how to complete the square? So we have basically have this. So if we add this squared to both sides, then now we have a complete square over here. So this would be t plus squared is equal to this stuff on the right. And now we can take the square root. And now remember, when you take the square root, it can be plus or minus, and we'll kind of see about that. And so we basically have plus or minus. Now, and notice here we have everything kind of over b squared. So I'll just skip a couple steps in here. And then, well, basically, so that's our, so in other words, we can unravel this equation to identify t, and now some issues arise. Of course, now we have two solutions here, and sometimes when you have two solutions, then one of them might be a little bogus. But in this case, is it reasonable that at least in some cases there would be two solutions? In other words, sometimes you have to kind of look at the geometry of it to figure that out. In other words, have we, sometimes, remember when you square things, sometimes you can introduce a spurious solution. And the question is, have we?
Wouldn't we need to be keeping track of the signs throughout to avoid that squaring, based on doing the positive side?
Well, yeah, in other words, well, where do we have to worry about the sign? There's only one place.
With the plus or minus part of it, could there be a situation where you end up with like a time that's less than when you entered the connection?
In principle, without delving further into it, in principle, yes. Yeah. In other words, can there be negative roots there? And the answer is absolutely. But just from the picture, do you see that two roots might be something which is possible? Yeah, in other words, what we're saying is we are saying that we were focusing on the enter point, and we said it was a place where we were exactly the maximum range away from the origin, which is where the sensor is located. But there's also another point in the picture where we're exactly r units away from the origin. And so based on the picture, it is not unreasonable that there would be two solutions. Now, let's come back to the question. Now, just in terms of the numbers, is it possible that these come up negative? Well, let's look at this situation. If this is the physical situation, then these had both better be positive. In other words, I'm starting moving here, and according to this, some time later, this will occur, and some time after that, this will be the situation. So the equation had better come up positive for both groups in that case. Otherwise, it's all bogus. Now, can you think of a situation where I might get negative roots? Well, what if, I have different colored markers, but okay, so what if, this is the picture, and I call this the canonical picture because this is where you can kind of see what's happening, but what if that isn't the picture at all? What if it actually looks like this? What if that is the situation? Well, the equations, the equation of motion doesn't specify whether t is positive or negative. And according to Einstein, at least, there's nothing in physics that says that time has to go forward or something. But so far, except in the movies and TV, they haven't done anything about that. But if this is the situation, then there were two times in the past where, if this had been the equation of motion for some time, then that means that I had entered and exited in the past. So in other words, if both of these roots are negative, which is entirely possible, this is the situation. I've started outside the range and I'm going away from it. And what that implies for the for a simulation that this is embedded in is that as long as I'm doing this, I don't have to consider anything about this sensor and this target. Because as long as this is the equation of motion for this target, there will never be a time when this sensor can possibly see it. So that means I don't have to do any more work unless the target turns around or something like that. So in other words, if I have two negative roots, then I know that the situation is that I'm outside the range and I'm moving away. Well, what if I had, is it possible to have a positive root and a negative root? Well, absolutely. And what is the situation there? Well, what if I started off in here and then went in that direction? So what is the situation there? The situation is that I would have a negative root, which means I entered in the past and I'm going to exit in the future. And how can I tell that from just the equations? Is that if I get a positive root and a negative root. So if I get two positive roots, then I know that this is the situation, that is I'm outside the range, and that means I can schedule an enter range based upon the smaller of the two roots. If this is the situation here, that is I get two negative roots, I don't have to do anything. That is, there's nothing to schedule because they're never, as long as everything stays the same here, then there's never going to be an interaction. If I get a positive root and a negative root, then I know that this is the situation, and so what I need to do is schedule an exit range based upon the positive root. Now there's one more issue here. Can this quantity always be computed?
No, the vector is 0 magnitude.
Yeah, well, yeah, so if I'm not moving, then, yeah, so assuming I'm moving, then can I always compute this? Why not? Yeah, the only issue is if I'm stationary, then, and if I'm stationary, that is if I'm not moving, then, so in other words, if I'm just sitting there, then what do I need to schedule in terms of this?
Nothing as long as the sensor isn't moving.
Yeah, well, again, yeah, we're stationary at the origin, and if this is stationary, then there's nothing to schedule. But apart from that, I can always compute this. Now, what about this? Is there an issue with taking the square root of something? Whenever you see a square root, you say, well, what if it's negative in there? Can that be negative? Well, yeah, no, in other words, but can that expression be negative? That's the question. No, that is,
Until the plus or minus sign makes it negative. Like you have to be able to solve that all the time.
yeah, well, the plus or minus, that is, if I try to take the square root of a negative number, again, I'm going to get an imaginary answer, and when we're moving around on a plane or anywhere, then I mean, imaginary numbers are imaginary only. I mean, they're not literally imaginary. They are real for some things, but not for this. In other words, is there a danger of computing this, what's under the radical, and having it come up negative? In which case, you know, things are going to. If you just try to do that, well, try it sometime. You know, you're gonna get an exception. Exceptions are not a good thing when you're running any kind of program. So is that something that you need to worry about? That is, taking the square root of this expression, will that expression, is it possible for that expression to be negative? Well, let's look at the pieces. So here, is it possible for the inner product of two vectors to be negative? Sure. Do you, like, what is the relationship of the two vectors if their inner product is negative? They're going back. Yeah, they're acute. Yeah, no, it's like an acute angle, right? So yeah, so that can be negative, but I'm squaring it. So once I square it, then even if the inner product is negative, then that expression is positive. The velocity squared, that's the speed, so that's always positive. But look at what we have here. We have this. Can this quantity be negative? Sure as heck can. Now the question is that negative enough to make the whole expression negative? Is that possible? That is absolutely possible. So conceptually, what does it mean if I have a quadratic equation for which there are only imaginary roots?
That is not on the plane.
It's moving in another dimension that
Yeah.
isn't.
Well, physically what's happening here is that, like in all of these, I've kind of drawn the trajectory of our unit so that it actually intersects this. What do you suppose I would get if that's the situation? So what is the solution? What is the solution to this equation if this is what's going on?
There's no solution.
There's no solution. And in a quadratic equation, how can I identify when there's, quote, no solution? How can I identify the situation where there, quote, is no solution?
You remember?
Well, if the expression in the radical is negative, in other words, if you remember remember it in general, e squared minus 4ac. Remember that sort of a generic thing. If that's negative, then I have imaginary roots. In other words, I'm trying to. This solution will be imaginary if this is negative, and if this is negative, that means that this is the situation. And these are the only possibilities. In other words, if I have a quadratic equation, there are only, well, one possibility is that there's no solution. And how could I identify whether there's no solution? By evaluating what's under the radical and seeing whether it's positive or negative. And if it's negative, it means I can actually end early because if this is the situation, so I got a sensor sitting there stationary, I got a mover that's kind of going like this, what event do I need to schedule in terms of entering or exiting range? What kind of interaction is this sensor going to have with this target if this is the situation? None. So in other words, if I get an imaginary solution, then I don't need to do any more work. At least for as long as this is the relationship between the two. On the other hand, so if I either have, for a quadratic equation, I either have no solutions or I have two solutions. If I have two solutions, then there are three possibilities. I get two positive solutions, in which case this is the situation. I get a positive and a negative solution, in which case I started off inside and I'm traveling outside. or I get two negative solutions, in which case I'm traveling away. So if I have two positive solutions, the next event to schedule, I can schedule an enter range with the delay of the smaller of the routes. If I get a positive and a negative, I can schedule an exit range with the positive route. If I get two negative routes, I don't need to do anything, and if I get all imaginary routes, again, I don't need to do anything. Okay, so this more or less summarizes that. So here's our solution based upon solving our equation of motion, and when it's exactly r units for the away from this stationary. And so again, if I have a smaller and a larger route, and that will typically be the case. In other words, if this first piece is, in other words, I'll typically have one smaller than the other, and I can schedule an enter range at the smaller of the two. If one is negative and the other is positive, then I can schedule an exit there. Then if they're both negative, then I'm moving away and I do nothing. And if I have complex routes, then I'm missing the range absolutely, and I do nothing. Okay, so what this solves, again, maybe in a way which involves a few complex computations, is that in the case where I have a stationary sensor and a target that starts moving at time 0, then I have a complete solution. Now, if that's all I can do, then it's not going to be terribly interesting, because in most situations, again, the natural question comes to mind, and I think this was mentioned a little earlier, well, what if they're moving? Then what? Okay, so let's assume that, or let's look at the situation where they're both moving. And now, this is a situation where solving the simplest case actually can be very helpful in terms of identifying the kind of the key element of what's going on, and then finding that it's fairly straightforward to extend it to the situation where they're both moving. And again, we're going to assume time 0. That is without loss of generality, because if you remember, all of the in this event language that we've been using, the times are all from the current time. And so I don't have to worry too much about, I mean, at some point I have to for certain calculations, but for this, I really don't. I can assume things are kind of at time 0. So, but I will assume that again, our equation of motion is going to be consistent. So let's say that I have a target and its equation of motion. It has a beginning location and a velocity. And my sensor is also moving. So my sensor started at a certain location and has a certain velocity too. So they're both moving. So the key element here now is the fact that any frame of reference is arbitrary. So far we've been looking at it from kind of a third-party frame of reference. But what if we looked at it from the sensor's frame of reference? So in the sensor's frame of reference, then we're stationary and everybody is moving around relative to us. So that's the narcissistic, egotistical perspective. And in a sense, we all have that to one degree or another. So I'm fixed, and everybody's kind of moving around me. So from the sensor's frame of reference, we are stationary at the origin, and now we just need to do things relative to our frame of reference. So in our frame of reference, the location of the target, again, if our sort of quote absolute location, in this case is XS for sensor, the target's location relative to us is simply the difference between their absolute location and our absolute location. So this is the the location of the target relative to the sensor. And since we're both moving at a constant velocity, the relative velocity we have is the difference of the velocities. And again, this is where you have to be careful and not look at the speeds, because the speed is a scalar, the velocity is a vector. So in the situation, for example, so even if they're both moving, if they're stationary with respect to each other, then that means that they're basically moving according to the same velocity. In other words, if my say my sensor is here and moving like this, and my target is here, and that's also moving at exactly the same velocity, then relative to the sensor, the target is stationary. And so we can apply our previous solution, substituting our x naught with our relative location and our velocity as the relative velocity. In other words, this solution that we did in the simplest case applies as long as we apply it to the right quantities. And in this case, the quantities are the relative location and the relative velocity. Okay, so here's an example. So supposing we had a target located at minus 30, 40, and moving at a speed of 40 clicks. And we have a target destination of 50 minus 20, and we have a sensor range of 20. So first we need to find, now here we're going to do this for the stationary sensor just as a, so we need to first find the velocity, and again we do the same calculation as before. We subtract the destination from our location. We find the norm, which has been concocted to come out evenly. That's because when you get to when you get to kind of specify the parameters, you get to kind of make it easy. So I have the luxury of making it easy myself, and if I ask you to do it, I'm going to make it hard on you. That's just my prerogative. So velocity again. So my distance vector made into a unit vector by dividing by the norm multiplied by the speed, and so I get a kind of a nice round number. Now my velocity squared, again, just as a check, is going to be the square root of b squared, and turns out to be 1600, which is also 40 squared. So again, that's just sort of an extra check on whether I've done that right. So now let's look at the inner product. Remember, the inner product, we multiply the two x coordinates and add them to the product of the y coordinates. And here we come up with a negative number. And if you think about it, remember that the inner product is related to the angle between vectors. There are kind of two ways of looking at it. One is this product of the coordinates, which is, for these calculations, is a more useful way of looking at it. But there's another way where it's the magnitude of the two vectors times the cosine of the angle between them. So intuitively, does it make sense that the inner product be negative? thinking of the cosine of the two. So again, what does it mean to have a negative inner product or a negative cosine? Yeah, in other words, they form an acute angle. So let's, if we think, so if we're here at the origin, and here's our x naught, our in this coordinate system, the x vector is that, and let's say if we are, our velocity vector is going to look like this, but remember, when we're looking sort of at vectors, where we kind of place it is kind of arbitrary. In other words, if we move this vector down here, we move the velocity vector to the origin, we see that it forms an acute angle with the target's vector in this coordinate system. Whereas if it were an acute angle, then that would mean, you know, we're kind of moving away a little bit more. So that's just sort of another little thing to look for. Again, the other elements we need are the square of that is the square norm of the x location. And then we want to compute the radical. We want to compute the quantity under the square root first to see whether or not we have extra work to do. If this comes up negative, then we can stop. But in this particular case, when we do the computation, it comes out to a positive value, and therefore we have two real roots. And so now, again, being, sort of laziness says, let's do this computation. If we can end early, we'll end early. We can't end early, so we need to do the next one. And now notice that because this inner product was negative, when we take the negative of that, that's going to turn it positive. And then when we do the computation of the second one, again, it just turns out to be this. So finally, we get our two roots, which are 1.2 plus or minus 0.357 approximately, which are 0.843. So the enter range will be at the smaller of the root. And so how can we figure out where the target is? Well, we simply plug in that time that is at the enter range. Now we go all the way back to the original equation of motion of the target, and that is where it's going to be. Okay, so, and why worry about this? And we need some means for checking the work, because as these computations are non-trivial, and so implementing them, it's not rocket science, but it's still a little bit more complicated than the kinds of things that we've been dealing with. So, for example, if I'm looking at a service time and I have a service time generator, I just generate. So that's easy. This, on the other hand, is a little bit more complicated, a little bit more work. And so if I'm implementing this, I need to test it in situations where I know what the answer is, having worked out the answer based upon these equations.